Welcome to Tech Girl Kannada YouTube channel.
Operating Systems Chapter 1 Introduction. What operating systems do? Computer system organization, computer system architecture, computer operating system structure, operating system operations, process management, memory management, storage management, protection and security, distributed systems, special purpose systems, computing environments, open source operating systems. Objectives: to provide a grand tour of the major operating systems components, to provide coverage of basic computer system organization. What is an operating system? A program that acts as an intermediary between a user of a computer and the computer hardware. Operating system goals: execute user programs and make solving procedure problems easier. Make the computer system convenient to use. Use the computer hardware in an efficient manner. Computer system structure. Computer system can be divided into four components. Hardware provides basic computing resources, CPU, memory, I/O devices. Operating system controls and coordinates use of hardware among various applications and users. Application programs define the ways in which the system resources are used to solve the computing problems of the users. Word processors, compilers, web browsers, database systems, video games. Users: people, machines, other computers. Four components of a computer system: computer hardware, operating system, system and application program, user. User 1, user 2, user 3, user n. Compiler, assembler, text editor, database systems, system and application programs, operating system, computer hardware. Operating system definition: OS is a resource allocator, manages all resources, decides between conflicting requests for efficient and fair resource use. OS is a common control program. Controls execution of programs to prevent errors and improper use of the computer. Operating system definition: no universally accepted definition. Everything a vendor ships when you order an operating system is good approximation, but varies wildly. The one program running at all times on the computer is the kernel. Everything else is either a system program, ships with the operating system, or an application program. Computer startup. Bootstrap program is loaded at power up or reboot, typically stored in ROM or EPROM, generally known as firmware. Initializes all aspects of system, loads operating system, kernel, and starts execution. Computer system organization. Computer system operation. One or more CPUs device controllers connect through common bus, providing access to shared memory. concurrent execution of CPUs and devices competing for memory cycles. CPU, disk controller, USB controller, graphic adapter to monitor, USB controller to mouse, keyboard, printer, online, disk controller, disks, CPU, memory. Computer system operations. I/O devices and the CPU can execute concurrently. Each device controller is in charge of particular device type. Each device controller has a local buffer. CPU moves data from or to main memory or to or from local buffers. I/O is from the device to local buffer of controller. Device controller informs CPU that it has finished its operation by causing an interrupt. Common functions of interrupts. Interrupt transfers control to the interrupt service routine, generally through the interrupt vector, which contains the addresses of all the service routines. Interrupt architecture must save the address of the interrupted instruction. Incoming interrupts are disabled while another interrupt is being processed to prevent a loss of interrupt. A trap is a software generated interrupt caused either by an error or a user request. An operating system is interrupt driven. Interrupt handling. The operating system preserves the start state of CPU by storing registers and the program counter. Determines which type of interrupt has occurred. Polling, vectored interrupt system. Separate segments of code determine what action should be taken for each type of interrupt. Interrupt timeline. CPU, user processing, executing. I/O interrupt processing, IDLE. Transferring. I/O device, I/O request, transfer done, I/O request, transfer done. I/O structure. After I/O starts, control returns to user program only upon I/O completion. Wait instruction idles the CPU until the next interrupt. Wait loop contention for memory access. Most one I/O request is outstanding at a time. No stimulations I/O processings. After I/O starts, control returns to user program without waiting for I/O completion. System call request to the operating system to allow user to wait for I/O completion. Device status table contains entry for each I/O device indicating its type, address, and state. Operating system indexes into I/O devices table to determine device status and to modify table entry to include interrupt. Direct memory access structure used for high-speed I/O devices able to transmit information at close to memory speeds. Device controller transfers blocks of data from buffer storage directly to main memory.
without CPU intervention. Only one interrupt is generated per block rather than the one interrupt per byte. Storage structure. Main memory, only large storage media that the CPU can access directly. Secondary storage, extension of main memory that provides large non-volatile storage capacity. Magnetic disks, rigid metal or glass platters covered with magnetic recording material. A disk surface is logically divided into tracks, which are subdivided into sectors. The disk controller determines the logical interaction between the device and the computer. Storage hierarchy. Storage system organized in hierarchy. Speed, cost, volatility. Caching. Copying information into faster storage system, main memory, can be viewed as a last cache for secondary storage. Storage device hierarchy, registers, cache memory, main memory, electronic memory disk, magnetic disk, optical disk, magnetic tapes. Caching. Important principle performed at many levels in computer and hardware, operating system, software. Information in use copied from slower to faster storage temporarily. Faster storage cache checked first to determine if information is there. If it is information used directly from the cache, fast. If not, data copied to cache and used there. Cache is smaller than storage being cached. Cache management, important design problem. Cache size and replacement policy. Computer system architecture. Most systems use a single general purpose processors PDAs through mainframes. Most systems have special purpose processors as well. Multi-purpose processors systems growing in use and importance, also known as parallel systems, tightly coupled systems. Advantages includes increased throughput, economy of scale, increased reliability, graceful degradation or fault tolerance. Two types: asymmetric multiprocessing, symmetric multiprocessing. How a modern computer works. Thread of execution, CPU, cache, device M, IO request, data, interrupt, DMA, instructions and data memory, cache to instructions execution cycle, data moment. Symmetric multiprocessing architecture are CPU 0, CPU 1, CPU 2, registers, cache to the memory. A dual core design, CPU core not CPU core 1, registers, cache, memory. Clustered systems like multiprocessor systems but multiple systems working together, usually sharing storage via storage area network SAN, provides a high availability service which survives failures. Asymmetric clustering has one machine in hot standby mode. Symmetric clustering has multiple nodes running applications monitoring each other. Some clusters are offer high performance computing HPC. Applications must be written to use parallelization. Operating system structure, multi-programming needed for efficiency. Single user cannot keep CPU and IO devices busy at all times. Multi-programming organizes jobs so CPU always has one to execute. A subset of total jobs system is kept in memory. One job selected and run via job scheduling. When it has to wait for IO devices, example, OS switches to another job. Compute operating system structure, time sharing, multitasking is logical extension in which CPU switches jobs so frequently that users can interact with each job while it is running, creating interactive computing. Response time should be less than 1 second. Each user has at least one program executing in memory process. If several jobs ready to run at the same time, CPU scheduling. If processes don't fit in memory, swapping moves them in and out to the run. Virtual memory allows execution of processes not completely in memory. Memory layout for multi-programmed system. Operating system job 1, job 2, job 3, job 4. Operating system operations. Interrupt driven by hardware, software error, or request creates exception or trap. Division by zero request for operating system service. Other process problems include infinite loop processes modifying each other, or the operating system. Dual mode operation allows OS to protect itself and other system components. User mode and kernel mode. Mode bit provided by hardware provides ability to distinguish when system is running user code or kernel code. Some instructions designated as privileged only executable in kernel mode. System call changes mode to kernel. Return from call resets to user. Transition from user to kernel mode. Time to prevent infinite loop process hogging resources. Set interrupt after specific period. Operating system decrements counter. When counter 0 generate an interrupt set up before scheduling process to regain control or terminate program that exceeds the allotted time. User process executing call system call trap mode beat 0 return from the system call execute system call. User mode, kernel mode. Process management. A process is a program in execution. It is a unit of work within the system. Program is a passive entity. Process is an active entity. Process needs resources to accomplish its tasks. CPU, memory, IO files, initialization data. Process termination requires a reclaim of any usable resources. Single threaded process has one program counter specifying location of next instruction to execute. Process executes instructions sequentially, one at a time until the completion. Multi-threaded process has one program counter per thread. Typically, system has many processes, some operating system running concurrently on one or more CPUs. Concurrency by multiplexing the CPUs among the processor threads. Process management activities. The operating system is responsible for the following activities in connection with process management: creating and deleting both user and system processes, suspending and resuming processes, providing mechanisms for process synchronization, providing mechanisms for process communication, providing mechanisms for deadlock handlings. Memory management. All data in memory before and after processing, all instructions in memory in order to execute. Memory management determines what is in memory when optimizing CPU utilization and computer response to users. Memory management activities. Keeping track of which parts of memory are currently being used and by whom. Deciding which processes and data to move into and out of memory, allocating and deallocating memory space as needed. Storage management. OS provides uniform logical view of information storage, abstracts physical properties to logical storage unit, file. Each medium is controlled by device disk drive. Varying properties include access speed, capacity, data transfer rate, access method, sequential or random. File system management. Files usually organized into directories. Access control on most systems to determine who can access what. OS activities include creating and deleting files and directories, primitives to manipulate files in directories, mapping files onto secondary storage, backup files onto stable or non volatile storage media. Mass storage management. Usually, disks use it to store data that does not fit in main memory or data that must be kept for a long period of time. Proper management is of central importance. Entire speed of computer operation hinges on disk subsystem and its algorithms. Voice activities, free space management, storage allocation, disk scheduling. Some storage need not to be fast. Tertiary storage includes optimal optical storage, magnetic tape. Still must be managed. Varies between warm, write once, read many times, and RW, read write. Performance of various levels of storage. Movement between levels of storage hierarchy can be explicit or implicit. Name, typical size, implementation technology, access time, bandwidth, MB or second, managed by backup by. Registers less than 1 KB, custom memory with multiple ports, CMOS 0.25 nanoseconds, access time 20K to 1 lakh, compiler cache memory greater than 16 MB, on chip or off chip, CMOS or SRAM 0.5 to 25 NS, 5K to 10K MB or second. Hardware management managed by hardware, backed by main memory. Main memory greater than 16 GB, CMOS DRAM 82 to 50 NS, 1000 to 5K bandwidth. Operating system disk storage greater than 100 MB, 100 GB. Magnetic disk 5000 XNS, 20 to 150 MB per second. Operating system CD or tape. Migration of integer from disk to register. Multitasking environments must be careful to use most recent value no matter where it is stored in the storage hierarchy. Magnetic disk to main memory to cache memory to hardware registers. Multiprocessor environment must provide cache coherency in hardware such that all CPUs have the most recent value in their cache. Distributed environment situation even more complex. Several copies of datum can exist. IO subsystem. One purpose of OS is to hide peculiarities of hardware devices from the user. IO subsystem responsible for memory management of IO, including buffering, storing data temporarily while it is being transferred. Caching, storing parts of the data in faster storage for performance. Spooling, the overlapping of output of one job with input of other jobs. General device driver interface, drivers for specific hardware devices. Protection and security, any mechanism for controlling access of processes or user to resources defined by the OS. Security, defense of the system against internal or external attacks. Huge range including denial of service, worms, viruses, identify theft of service. Systems generally first distinguish among users to determine who can do what. User identities, user IDs, security IDs include name and associated number, one per person, user. User ID then associated with all files, processes of that user to determine access control. Group identifier, group ID allows set of users to be defined and controls managed, then also associated with each process file. Privilege escalation allows user to change to effective ID with more rights. Computing environments. Traditional computer blurring over time. Office environment. PCs connected to a network, terminals attached to mainframe or mini computers providing batch and time sharing. Now portals allowing networked and remote systems access to same resources. Home networks used to be single system, then modems, now firewalled, networked. Computing environments count client server computing, dumb terminals supplanted by smart PCs. Many systems now service responding to requests generated by clients. Compute servers provides an interface to client to request services. Fire server provides to store and retrieve files. Client are in the bus along with the server network. Peer-to-peer computing, another model of distributed system. P2P does not distinguish clients and servers. Instead, all nodes are considered peers. May each act as client, server, or both. Node must join P2P network. Registers its service with central lookup service on network or broadcast request for service and respond to request for service via discovery protocol. Examples include Napster and Nutella. Web-based computing. Web has become ubiquitous. PC's most prevalent devices. More devices becoming network to allow web access. New category of devices to manage web traffic among similar service. Load balancers. Use of operating systems like Windows 95 client side have evolved into Linux and Windows XP, which can be clients and servers. Open source operating systems. Operating systems are made available in source code format rather than just binary closed source, counter to the copy protection and digital rights management movement started by Free Software Foundation FSF, which has copyleft GNU public license. Examples include GNU or Linux, BSD or Unix, including core of Mac OS X and Sun Solaris. Thank you for watching. Do like, share, and subscribe to my channel.